So what I want us to start with, I want us to start with those two algorithms. Then after we discuss those two algorithms, we can adjourn that class up to next week, where we will be discussing about subnetting. That is the class that I want us to have on next week. That is from Monday. So please tell others to be keeping time so that we can discuss some other things that we have not discussed, which are not even in your course outline, that we can discuss for our own knowledge. And maybe to start with, if you can remember, there is this algorithm that is mostly used for processing. And we need to ask ourselves, when you are using this algorithm, which is the best route that you can use in order to make sure that you can work, or maybe we can be able to work with a specific distance from a given route. Remember, in this point, we are looking at routers. And when you're using a router, I remember that there is a discussion on where we said we can look at an assignment on routers. And if you look at one of the routers, it was about forwarding routers and distributed routers. And out of those routers are the ones that now we are looking at now, which is the shortest distance that you can have. And when you look at the shortest distance that you can have, we will be able to understand this is the best route to use. So when we are using deconstruct, it is also called the greedy algorithm. The greedy algorithm. Because when you're talking about the greedy algorithm, we are talking about the algorithm that can take a shortest route possible. It is not looking at other, maybe it is not looking at other possible routes that we can have, because there might be another possible route that we can have, which will still be discussed by what you call the Bellman algorithm, or which is called dynamic algorithm. So I want to start with the presentation of the routes that we can have. And suppose we have the first point that we are supposed to move from. Then when you're moving to this, we have the second point. So this is the distance. So the distance that is supposed to be covered, maybe we are taking it supposed to be covered with 2. This becomes 2. Then from this point, we have another distance, which is another distance, which is supposed to go to distance number 4. And this distance number 4 is supposed to take 7. Then we have another one, which is supposed to be maybe 3, which is 3, supposed to take 4. Then we have another one. Then this one is supposed to take maybe 1. Then we can have maybe another one, which is supposed to be 5, which is supposed to take 3. Then this is supposed to go to have another distance, which is supposed to take 2. Then we have another one, which is supposed to be 6. Then this one is supposed to be 1. So in this case, what we need to look at, we can try to understand how are we supposed to move from a given point. So remember, this is the destination point, and these are the selected vertex. These are the selected vertex. And this is now the distance. This is now the distance. So in this case, we can assure that, let's say maybe the selected distance, like now if you look at now from the first point, which is 1. So we move to 2. Then this one is still moving to maybe 4. This one is still moving to 4. So in this case, we can say the vertex that we are supposed to have is 1, 2, and 4. But we have a distance. If you are moving from vertex maybe X, and then we are moving up to vertex U, maybe if you move to that. So if you can say if the distance of X from X plus the vertex of XU, the vertex of XU, so we are looking at V. The vertex of XU is less than the distance of X, the distance of U, sorry. The distance of U. Now, we say that is the best route that we can have. So if the distance of X, which is this, which sometimes we can say the distance is given as 0, for now, the distance of X is given as 0, plus the vertex of X and Y, that is now the distance that is covered from X to Y. So it will be 0 plus 1. If this one is less than the distance that is in U, where the distance that is in U, it can be determined by different routes that we are having. Remember, we can have this route that is moving from 1 to 2, then from 1 to 3. Suppose we have a distance that is moving from 3 to 2, and there is 1 to 2. So if you take the shortest distance, that is why we are saying that is the cover that we can have within this. And that's why we say the dV, the du that we are having here is equals to the d of x, plus the distance that we are supposed to cover on that vertices. So we can say vertices of x xu. So what we are saying is that we can now take, if this is the shortest distance, let us now replace with the shortest distance that we are having. Let us replace with that. And that is now the case that we need to understand when you're coming up with the calculations for this case. And maybe allow me to move to the next page so that I can now present on how we can be able to come up with this distance. Maybe we take the shortest path that we can have and we replace with the one that we are supposed to have here. So when you say if dx, that is the distance which is 0, plus the vertices of x and u, which is supposed to start from this point up to this point. So the distance that is covered here, plus that, if it is less than that, now you can take that distance. But if it is not less than that, we can replace that. That's why we are replacing with the shortest distance that we have. So in this case, this is what you call relaxation. This is what you call relaxation. So we need to calculate the relaxation of this graph. So relaxation is given by the shortest distance, looking at all possible routes that we are having. But if you look at this de Castras algorithm, we are not looking at other possibilities that we can have, because we can still have other possibilities that can also result to this distance that we are having. So let us try to move to the next page so that I can explain on how we should be able to come up with that. So allow me to draw it again, because in this case we cannot copy. So this one we have 2. And the distance that was covered here was 2. Then we had 4. So I've not clearly drawn that. So this one is supposed to cover 7. Then this is 1. So this is supposed to be 6. So there is another one that is moving to this, which you can call it 5. Then we have that. Then this is 5, if I can remember. So this is 2. Then we have 3, which is supposed to move to this. Then we have that, which is 3, which is 1. Then which is 4. So for this case, we have said if we are having this distance from 1, then we have distance 2. Allow me to use a mouse for now. So if you are having that distance that you are supposed to move from a given point, so we are saying if this is the distance, maybe we call it x, and this is u. So we are saying if the distance of x, which currently we can say it's 0, plus the vertices of x into u is less than the distance of u, Now we can take that root and we can now replace that. We can now replace that with d into u is equals to d of x plus the vertices of u and x. The vertices of u and x. So we can say, if this is the first distance, which is, if we are starting this is now the distance that we have already selected. And we know that this distance is 0. If this is the one that we have already started, this index is infinite. So all these distances are infinite. All these vertices are infinite. So we need to replace these infinites that we are having. And the first root that we are supposed to look at is from 0 to 2. So we have said we add the first distance, which is 0, plus 2. So for this one, you can replace with 2. Remember, we must use the arrows. We cannot add from 3 to 2 because the distance is coming from 2 to 3. So you should be able to note these arrows are pointing to where we are moving to. From 1 to 4 to 3, we are now taking, we replace this distance, and we are supposed to replace this distance with 4. So we replace this distance with 4 because now we have said, so this one we replace with 4. And this one we have already replaced with 2. So for this case, we have added 0 plus 4. That is now this infinite. We cancel that infinite. And now the infinite is supposed to be 4. Remember, there is a distance that is supposed to be covered from 2 to 3. And when you add 2 plus 1, it is supposed to be 3. So you look at the distance that is smaller than the other. So this 4, you replace with now 3. You replace with 3. Then you're supposed to move from 3 to 5. From 3 to 5, you need to replace this infinite. And for you to replace this infinite, we are supposed to add 3 plus 3, which is 6. Then from 5 to 4, and there is another distance from 2 to 4. When you take the first distance, 2 to 4, it is 9. It is 9 by replacing that infinite. But when you take from 5 to 4, it is supposed to be 6 plus 2, which is 8. So is 9 less than 8? 8 is less than 9. So you replace that with 8. So already now, I can take the distance from this infinite that I'm having here. I can use those two roots because that's why we are saying shortest distance. So we are saying 6 plus 5 is 11. But for this case, it was 1. Remember, it was 1. So 8 plus 1, so you replace this with 9. So in this case, we can say the selected vertices and now the distance that is covered. So the selected vertices, we have vertices 1, we have vertices 2, we have vertices 3, we have vertices 4, we have vertices 5, and we have vertices 6. So out of these, vertices 1 is the one that we are having 0. The other vertices 2 is the one that we are having 2. Vertices 3, we are having 3. Vertices 4, we are having 8. And vertices 5, we are having 6. And vertices 6, we are having 9. So that is now the possible routes that you can use using what you call the Dijkstra algorithm. But if you look at this, we have already taken the shortest relaxation because we have said when you are moving to this point, that is what you call relaxation. So we have taken the shortest route. But for this case, the relaxation that we have here, we are not looking at all possible routes that we can have. Remember, we are supposed to move with the possible routes that automatically, if you move again, we cannot get the smallest route or the possible route that we can have within a given point. So that is the way that we are supposed to calculate what you call the Dijkstra algorithm. Is there any question up to that point? Is there any question? Please, you can ask before we proceed. Have you understood? Okay, there is no question. Ian, Evans, are you in class? Evans Kotut. Okay, so if you look at the next one, we are saying that the next one is just a minute. So the next one was the bell. The next one was the Bellman-Ford. And this is still talking about the shortest distance or the shortest path. It is still talking about the shortest path, but in this shortest path, it should be what you call dynamic. It should be dynamic, meaning it should keep on changing. So we are looking at the shortest distance until we are exhausted with that shortest distance that we have. And for this case, I will still use the same diagram that I had. 1, we had 2. Then we can do another question so that we can try to understand all that. This is 3. So this is 1, 4, 2. We have 4. This is 7. 5. 6. So this is 1, 5. So for this case, you must have what you call pairs. And we can say the selected vertices is equals to 1, 2. Then we have the next selected vertices is 1, 4. 1, 4. The next selected vertices is 2, 3. 2, 3. The next selected vertices that we are supposed to have is 2, 4. The next selected vertices that we are supposed to have is 3, 5. The next selected is 4, 5. The next selected vertices that we are supposed to have is 4, 6. And the next one that we are supposed to have is 5, 6. So at this case, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. That is what we are supposed to have on that. Then for this case, we look at now the distance. Already this one is given as 0. So yes, I can see you are typing, Evans. I'm waiting for your question so that you can proceed. Okay. Oh, when we are selecting pairs, you're not, you don't follow any path. You don't follow any procedure. The only thing that we are supposed to follow is that we are supposed to follow these distance or these arrows. So this arrow is pointing from 1 to 2. You take the first one. The next one that is supposed to be taken, it is 1 and 3 because the arrow is pointing from 1 to 3. Then the next one is 2 to 3. So we are through with this. We can even move to this 2 to 4. And we select the distance that is supposed to be covered, pointing to 4. Then from 4 to 5, we can still use that, or we can use 3 and 5. So in this case, we are having two distances, 3 and 5. Then we can have 4 and 5. Remember that the arrow is pointing to 5. Then the next one that you can have is 4 to 6 and 5 to 6. So you must make sure that you exhaust all the arrows that we are having, all the points that we are having. 1, 2, 3, 4, 5, 6, 7, 8 arrows. And that's why I have counted 1, 2, 3, 4, 5, 6, 7, 8. Is that okay, Evans? Have you now understood all that? So we must follow, as long as you are taking them or you are selecting them. Where is 1 and 4? Ian, we cannot take 1 and 4. This is the distance. We are using vertices or vertex. We are using vertex. And we have vertex 1, we have vertex 2, we have vertex 3, then vertex 4 comes here now. So this is the distance. So I think I was supposed to change this with another color maybe. So this is supposed to be 2. This is supposed to be 4. This is supposed to be 7. This is supposed to be 1. 1, 2. So with blue, these are distance, but these are vertices. Are you okay, Ian? Are you okay, Ian? Before I proceed. So we are taking the vertices from 1 to 2. Well, we know that currently the distance of 1 is 0 because we have not moved. The distance of 2 is 2 because we have moved from 1. The distance of 3 is given as 4. The distance of 5 is given as 3. The distance of 5 from 4 to 5 is given as 2. I can't understand your question. Oh, sorry. Oh, might be you are asking because of this question. Oh, I'm sorry. So we have 1, 2. This is 1, 3. I'm sorry. Maybe this one is the one that had an issue. I'm sorry. Is it okay now? I'm sorry for that. Is it okay now? Okay. I'm sorry for that. I'm sorry. We have 1, 2, 3. 1, 3. Then we have 1, 2, 1, 2, 1, 3, 1, 3. Then we have 2, 4. 2, 4 is given. Then we have 2, 3. 2, 3 is given. 3, 5. 3, 5 is given. Then 4, 5. 4, 5 is given. Then we have 4, 6. 4, 6 and 5, 6. I think that is okay now. Now, for this case, we want now to get the distance. Remember, these are all infinites. These are all infinites. Remember, for now, these are all infinite because we have selected the distance to start from here. And because we have already selected the distance to start from there, now you have to look at now the best possible route that we can have. So in this case, we want to replace this infinite. So you want 0 plus 2. This becomes 2. Then 0 plus 4. This becomes 4. Then remember that there is another distance here, which is supposed to move from 2 to 3. And there is 1 to 3. So you need to look at the smallest distance. So for you to look at the smallest distance, now you have to take from distance 2 to 3, which is 2 plus 1, that is 3. So you replace that with 3. We replace that with 3. The next distance is 2 to 4. We take 2 to 4. So 2 to 4. 2 to 4 is supposed to be 9. 2 to 4 is supposed to be 9. Then the next one is 3 to 5. 3 to 5. So when you're moving 3 to 5, we're supposed to take 3 plus 3, which is 6. First, we replace that. Then there is 4 to 5. 4 to 5. That is 9 plus 2. That is 11. So because that is now less, 6 is less than 11, sorry. Now we retain 6 here. So for this case, the infinite is supposed to be replaced with 6. Then we are supposed to move from 5 to 6. That is 6 plus that, it becomes 11. So for this case, we're looking at now, the distance from 5 to 6 is 11, but we have another distance which is 4 to 6, which is supposed to be 9 plus 1, which is 10. That is what is given. So we replace this 11 with the 10. Remember, we are not through with the exhaustion. We must make sure that we pass through another step or another move until we get that now we have the shortest distance possible. And that is now the distance that I want to move to. So for this case, we can move from 1 to 2. 1 to 2. Remember, 1 to 2 is still 2. The distance is still catered for. So we are now retaining it to 2. Then from this case, we move from 2 to 3. From 2 to 3, which is supposed to be 2 plus 1, which is 3. Then here was supposed to be 1 plus 4. It is, so you retain the distance the way it is. Then we move from 2 to 3. And already we have done that. Then 2 to 4. 2 to 4. Remember, for you to move 2 to 4, we are supposed to take this 2 plus this 7, which is supposed to be 9. So the distance is still okay. We retain the distance the way it is. Then the next one that we are supposed to move is 3 to 5. So 3 to 5, we move from 3 to 6. Then we find that it is supposed to be 6. We retain the same distance because 9 plus 2 is 11. Then after that, we move from 5 to 6. When you move from 5 to 6, we are supposed to take 6 plus 5, which is supposed to be 11, and this is supposed to be 10. So we look at now, even if we move 2 times, we are still getting the same distance. Even if we move the same 2 times, we are still getting the same distance. So for this case, we cannot change our route. The route remains like that. But the first thing that you're supposed to notice, first of all, pair the distances. You pair the distances. When you pair the distances, you'll be able to come up with a clear presentation. I want us to do another question before you ask a question so that we can try to maybe understand the case. So I will use the same presentation, another presentation. So for this one, we have 2. This one is supposed to be 3. It's supposed to be 3. Maybe we can have another one. So it depends with the routes that you want to have. You can have your own route, which is 4. And there is this. So if you can look at the distance that are covered there, we have a distance of 3. We have a distance of 5. We have a distance of -3. We have a distance of 2. So let's use the Bellman. Let's use the Bellman. And when you're using this Bellman, we must first of all pair the distances, the vertices. So vertices, pair the vertices, which is supposed to be, these are what you call the selected vertices. Selected vertices. So we have 1, 2. Then we can have another selected vertices, 1, 4. 1, 4. We can have another one, which is 4, 3. And we can have another one, which is 3, 2. which is 3, 2. Which is 3, 2. So for this case, I don't know whether that color is okay. So we can look at now from the first distance, this is 0. So 0 plus 3, that becomes 3. So remember, these are all infinites. These are all infinites that we are having. So we must replace them. So we have 0 plus 5, that is 5. Then for this case, we are supposed now 5 plus 2, which is 7. Which is 7. So for this case, there are two ways that you can move to this. So 0 plus 3 is 3, and then we have 7 minus 3. 7 minus 3 now becomes 4. It becomes 4. So automatically it is retained. So if the negatives on the negative side is greater than on a positive side, now you retain the way it is in that form or in that forum. Then we start moving again from 1 to 2, 1 to 2. So we are taking 0 and 3. You take 0 and 3. Then we move from 1 to 4, 1 to 4. We still have the same distance. That is okay. And that is still okay. Then from 4 to 3, remember 4 to 3 is supposed to take 5 plus 2, which is 7. It is still okay. Then for this case, we have to take 7 minus 3, which is 4. So this is given by the first turn of execution. Let's try to complicate this because this is very simple. Let's maybe try to complicate this, and maybe we can have 1. Maybe we have another 2. Maybe we can have maybe 4. Five. So 1, 2, 3. Sorry. There is something that I wanted to complicate on that. So let me try to start again. That is the problem with this, you cannot rub. So 2, 4, so this arrow is not pointing to this. This arrow is pointing to that. So that arrow is pointing to that. This one is pointing on this. Then we can have 6 somewhere here. And maybe we can have a distance on this, which is 35. Maybe this is that. So for this case, we have this is 10. This is 50. This is 15. 10. 15. 3. So we now first of all start by pairing the distances. So we have 1, 2, 1, 4. Then we have 2, 4. Two, 4. Then we have 4, 5. Then we have 5, 2. Then we have 2, 3. And the last one is 6, 4, 6, 5. Remember, these are only presentation of an alternative directions, alternative distances that we are having. So within this case, we can either use this route from 5 to 6. So we can have another one from 3 to 5. And we can have another one from 5 to 3. 5 to 3. So those are distances that we have given on that. So for this case, now we can start with the first one, which is supposed to be 0. This is supposed to, this infinite is, remember, these are all infinites. These are all infinites for now. So this becomes 50. From 1 to 4, 1 to 4, this becomes 10. 2 to 4, 2 to 4. So remember, 2 is 50 plus 15, that becomes, this one is greater than this, so it retains that. Then 4 to 5, 4 to 5, that is now supposed to be 25. Then remember, there is a distance that is not covered here. Let me give it 20. So 25 plus 20, that is 45. So you replace that with 45. Then from 25 to this, 45 plus that, that is 55. What is 25 plus that becomes 60, so you retain the distance as this. Then the next one is supposed to be from 3 to 5. 55 plus that, this becomes 80, so it retains that. Remember, this distance is not supposed to be covered by anything. So this will always remain as infinite. It will always remain as infinite because there is no distance that is moving from this point to this. So we cannot have a distance that is supposed to be covered. So this vertex, that vertex will always remain to be infinite forever. The next thing is now to move back. We see whether we can have another route on that, which is lesser than that. So we move from 0 to 1. So from 1 to 2, 1 to 2, 1 to 2, that is 50. Remember, currently it is 45. Currently it is 45. So it is supposed to be retained the way it is as 45. The next one is 1 to 4. 1 to 4 is 10. 0 plus 10, that is 10. Then 2 to 4. Remember, we are taking now 45 plus 15. So 45 plus 15, that is 60. So we have 60, but now it was 10. You retain the 10 as it is. Then from 4 to 5, having 10 plus that is 25. It is the same. And then we now need to move from 5 to 2. that is 25 plus 20, that is 45. It is still okay. Then from this to this, it is 45 plus that, it is 55. Then from 25 to this, which is now supposed to be 35, which is supposed, so this retain the same things. So the difference between the Bellman and Gcastra is that in Gcastra, we are only looking for a single path. We're only looking for a single path. But this one, we are looking for a multiple path. Multiple path in that we need to have a defined number of selections. So we are not exhausting to only one type of selection. We are not exhausting to only one. We can have multiple presentations. And this multiple presentation is the one that now results to a better way of understanding the scenario in this. And we'll be able now to have a very clear path, which is the best path to use, which has to use the simplest route in this execution. I want us to do another question. If there is a question, you can ask before I go to another question using the Bellman, because that is where we have some complication. Because sometimes you'll find there is a question that requires you to move maybe 4 steps or 10 steps so that we can come up with a better path. So this is not the best algorithm to use than when you are using the Gcastra. So most of the routers use the Gcastra's algorithm so that they can be able to use the simplest route possible. But you find that when you use the Bellman, we are having a very accurate path in terms of presentation, but we take long. But when you use this, there are some other data paths that will be retained within the path, which will not be exhausted. We will never be exhausted at a given point. So in this case, that's why we always look at a point where we use the Gcastra because of time consuming, but it is not all that best in terms of giving you the results that you are supposed to give you. So you look at there are other possible routes that you are supposed to take, but for this case, we are only looking for one or a single route that you can have within the presentation. So is there any question that you have maybe before I proceed? So can I go to the next example? Then we can adjourn our class. So as I wait, let me be drawing this diagram. Maybe we have the first one. As you ask the question, I'm waiting for your question. This is supposed to be 6. Three. This is, we can look at this arrow point to this direction, which is -2. And don't say 2 minus -2. So it is supposed to be negative. So we retain the way it is. So this becomes another path. Maybe we can give it 2. This is 4. And give is 5. There is an issue on that. So we can have -2. For this one, we can have -1. This one we have 1. -6. -1. 7, 3. Maybe 3. So you look at all possible paths that you are supposed to have. So we have 1, 2. We have 1, 3. Then we have 1, 4. Then we have 2, 3. Sorry, not 2, 3. This is 3, 2. Remember the arrow is pointing to 2. So this is 3, 2. Then we have 4, 3. Then we have 2, 5. 2, 5. Then we have 3, 5. Then we have 4, 6. Then we have 5, 7. And we have 6, 7. 6, 7. So those are possible paths that we are supposed to have. So in this case, there is 0. So this remain to be 6. This infinite remain to be 6. This is, we are supposed to move from 1, 3. 1, 3. This is supposed to be 2. Then we have 1, 4. 1, 4. Which is this supposed to be 5. Then we have 3, 2. 3, 2. Where this is 2 plus this. This minus this becomes 0. But if you look at this, we are moving from 4 to 3. 4 to 3 first. 4 to 3. So 5 minus that, this becomes 3. So it is retained the same. So this one is retained to be 0. So that one is 0. Then from this point, we are now supposed to move from 4, 3. That is okay. 2, 5. 0, that. So this becomes negative 1. That becomes negative 1. Then from there, we are supposed to move from 3 to 5. So this is 2 plus 1, that is 3. So you retain with negative 1. 4 to 6. So this becomes 4. This becomes 4. And 4 to 3, this becomes 1. So this minus that becomes 2. So it is retained as the same. So this one we will not change on that. So 2 minus 1, it retains as that. So this one we will not change. So in this case, we have gone the first path. So maybe we move the second thing, where the second one. From 0 to 2, we have 6. But currently we have 0. So you retain the way it is. So we are moving from 1 to this. So this is 0 plus that becomes 2. 2 plus 2 minus this becomes 0, which is already given on that. 5 minus 2, which becomes 3. So automatically we have 2, so this is less. So 0, currently it is 0 minus this. This is negative 1. And 2 minus this, minus 1 becomes 1. So that remains the same. So if you look at this, we are only moving to one distance on that, one move on that. So I think we can, if maybe you have a question you can ask, then we'll be able to do other questions next week as we do subnetting. So the next class we will be subnetting. And when you'll be doing some dating, you'll revisit this part when you have some negatives so that we can try to understand more on that. So the next thing that we are supposed to do, we are supposed to move to the question, to the examination room, and you do the questions that I have already posted so that now we can see whether we are understanding what we have already covered in that. So can we move to the examination room? Can we move to the examination room? Any question up to that point? I will start from this. We will have other questions that we will do on Burma. So can we move to the question room or to the examination room? I'm waiting for a question. Yes, I'm waiting for a question. Does it mean that Muko Kakras?